Right now, as you're watching this video, you're sitting on a planet that orbits at exactly the right distance from a perfectly sized star. Your atmosphere contains precisely the right mix of gases to keep you alive. Your planet's magnetic field deflects deadly cosmic radiation with mathematical precision. The water you drink exists in liquid form because of temperatures that fall within an impossibly narrow range, and every single breath you take depends on physical constants that are calibrated to such extraordinary precision that changing them by even the tiniest fraction would make your existence impossible. Tonight, we're exploring a question that has captivated scientists, philosophers, and anyone who has ever looked up at the stars and wondered about their place in the cosmos. Before we dive into what might be the most profound puzzle in all of science, I'd love to know where you're tuning in from and what first made you curious about our cosmic situation. And if you find yourself drawn to these fundamental questions about reality itself, I'd be grateful if you gave this video a like and perhaps subscribe to join our community of cosmic explorers. Let's get going. The story begins now. Tonight we're investigating a possibility so extraordinary that it challenges everything we thought we knew about accident and intention in the universe. What if Earth wasn't the product of random cosmic processes, but something far more deliberate? What if the conditions that make life possible weren't lucky coincidences, but evidence of cosmic engineering operating on scales we're only beginning to comprehend? This isn't science fiction, though it certainly sounds like it. This is cutting-edge physics and cosmology, grappling with observations so precise, so mathematically elegant, that they've forced some of the world's most brilliant scientists to confront uncomfortable questions about design, purpose, and intelligence in the cosmos. The numbers we're about to explore together will challenge your assumptions about randomness and necessity. They reveal a universe balanced on a knife's edge, where the slightest deviation in any of dozens of fundamental parameters would result in a cosmos completely incapable of supporting stars, planets, chemistry, or consciousness. We're talking about precision that makes the most sophisticated human engineering look crude by comparison. Imagine trying to throw a dart from Earth and hitting a bullseye the size of a coin somewhere near the edge of the observable universe. That begins to capture the mathematical accuracy required for our universe to support life. But here's where things get beautifully complicated. The same observations that suggest cosmic design also provide the foundation for alternative explanations that are equally mind-bending. We might live in one of countless universes, each with different physical laws. We might be witnessing the inevitable result of natural selection operating on cosmic scales, or we might be asking the wrong questions entirely, trapped by cognitive biases that make design seem more likely than it actually is. By the time we're finished tonight, you'll understand why this scientific puzzle has split the scientific community into camps that seem irreconcilable. You'll see why some Nobel Prize winners have concluded that the evidence overwhelmingly points to intelligent design, while others with equally impressive credentials argue that apparent design is nothing more than an illusion created by our limited perspective. The journey we're about to take together spans the smallest scales of quantum mechanics to the largest structures in the observable universe. We'll examine the fundamental forces that govern reality and discover why their precise values seem impossibly calibrated for complexity and life. We'll explore Earth's position in space and time, revealing layer after layer of conditions that had to be exactly right for you to exist and contemplate your own existence. This investigation will take us deep into what scientists call the anthropic principle, one of the most controversial ideas in modern physics. This principle suggests that the universe's apparent fine-tuning might be explained by the simple fact that we're here to observe it. But as we'll see, this seemingly straightforward idea opens up philosophical rabbit holes that connect quantum mechanics to theology, probability theory to the meaning of existence itself. We'll meet the physicists and cosmologists who first recognized these extraordinary coincidences in nature's fundamental constants. We'll follow their detective work as they uncovered layer after layer of apparent design, from the nuclear forces that hold atoms together to the cosmic expansion rate that determines whether universes collapse or expand into empty coldness. You'll discover why the production of carbon, the element that forms the backbone of all known life, requires such precise calibration of nuclear physics that one of the scientists who figured it out declared the evidence overwhelmingly pointed to a super-intellect. We'll explore why the cosmological constant, which governs the universe's expansion, appears to be fine-tuned to a precision that physicists describe as the worst theoretical prediction in the history of science. But we won't stop at the evidence for design. We'll dive deep into the alternatives, exploring multiverse theories that suggest our universe is just one of countless others, most of which are sterile and lifeless. We'll examine whether these theories solve the fine-tuning problem or simply push it back another level. We'll investigate new experimental approaches that might actually test these seemingly untestable ideas. The stakes of this investigation extend far beyond academic curiosity. The questions we're exploring touch on the deepest issues of human meaning and cosmic purpose. If the universe is designed, what does that mean for how we understand our place in the cosmic order? If it's not designed, what does that say about the role of intelligence and consciousness in an apparently random universe? These aren't just abstract philosophical puzzles, they're questions that affect how we think about scientific methodology, the nature of explanation, and the limits of human knowledge. They force us to confront whether science can ever answer ultimate questions about existence, or whether some mysteries lie forever beyond the reach of empirical investigation. Tonight's exploration begins with a single, seemingly simple observation. The universe we inhabit appears to be exquisitely calibrated for the existence of complexity, structure, and life. This observation has been confirmed by decades of careful measurement and theoretical analysis. The question that divides scientists is what this apparent calibration means. Let's start our investigation by examining just how precise this cosmic calibration actually is. We'll begin with the fundamental forces that govern all physical processes in the universe. There are 4 such forces: gravity, electromagnetism, and the strong and weak nuclear forces. Each of these forces has a specific strength that determines how particles interact with each other. The relative strengths of these forces had to fall within incredibly narrow ranges for our universe to develop the structures we observe today. Consider gravity, the weakest of the 4 fundamental forces. If gravity were slightly stronger relative to the other forces, stars would burn out quickly, leaving insufficient time for complex chemistry to develop on planetary surfaces. If gravity were slightly weaker, matter wouldn't clump together efficiently enough to form stars and galaxies in the first place. The precision required becomes staggering when you examine the actual numbers. The strong nuclear force, which holds atomic nuclei together, is about 10,000 billion times stronger than gravity. If we imagine this enormous range of possible force strengths as a ruler stretching across the entire observable universe, then changing gravity's strength by just 1 inch on that cosmic ruler would make life impossible. This isn't an isolated example of fine-tuning. The electromagnetic force, which governs the interactions between charged particles, must also be calibrated with extraordinary precision. This force is characterized by something called the fine structure constant, a dimensionless number approximately equal to 1 divided by 137. If this constant were even slightly different, atoms couldn't form stable chemical bonds, making complex molecules impossible. The fine structure constant determines how tightly electrons are bound to atomic nuclei. If it were larger, electrons would spiral into the nucleus, making chemistry impossible. If it were smaller, Electrons would be too loosely bound to form the stable configurations needed for complex molecules. The window for stable, complex chemistry appears to be remarkably narrow, but perhaps the most dramatic example of apparent fine-tuning involves something called the cosmological constant, which governs the rate at which the universe expands. Quantum mechanics predicts that empty space should be filled with a certain amount of energy, creating a repulsive force that accelerates cosmic expansion. The problem is that quantum theory predicts this energy. Density should be about 120 orders of magnitude larger than what we actually observe. This represents the largest discrepancy between theoretical prediction and experimental observation in all of science. If the cosmological constant had the value that our best theories predict, the universe would have expanded so rapidly that no structures could ever have formed. No stars, no galaxies, no planets, no life. The fact that the cosmological constant has instead exactly the tiny value needed for structure formation has been called the worst theoretical prediction in the history of physics. These examples represent just the beginning of a catalogue of apparent cosmic coincidences that seems to grow longer with each advance in our understanding of fundamental physics. The masses of elementary particles, the rates of nuclear reactions, the properties of dark matter, and dozens of other parameters all appear to be set with precision that defies explanation through chance alone. The situation becomes even more puzzling when we examine how these various parameters interact with each other. It's not just that each force or constant must be finely tuned individually. They must be finely tuned relative to each other in ways that create a web of interdependent relationships. Change one parameter, and you typically need to adjust several others to maintain the delicate balance that makes complexity possible. This interconnectedness suggests that if our universe were designed, the designer would need to possess an understanding of physics that far exceeds our current knowledge. The precision required seems to demand not just intelligence, but a form of superintelligence capable of calculating the consequences of adjusting multiple cosmic parameters simultaneously. Yet for all the apparent evidence of design in the universe's fundamental structure, we haven't even begun to examine the specific conditions that make Earth itself suitable for life. Our planet occupies what astronomers call the habitable zone around our star, the narrow range of distances where liquid water can exist on a planetary surface. This zone is sometimes called the Goldilocks zone, not too hot and not too cold, but just right for the chemistry of life as we know it. But Earth's habitability depends on far more than just its distance from the Sun. Our planet's size gives it sufficient gravitational pull to retain a substantial atmosphere while remaining small enough to avoid capturing excessive amounts of hydrogen and helium that would create crushing surface pressures. Earth's rotation rate creates day-night cycles that moderate temperature extremes. Our planet's axial tilt produces seasonal variations that may have been crucial for the evolution of complex life. Even more remarkably, Earth possesses a powerful magnetic field that deflects harmful cosmic radiation and solar particles. This magnetic field is generated by our planet's molten iron core, which itself depends on Earth having exactly the right size and composition. Without this magnetic shield, our atmosphere would gradually be stripped away by solar wind, as appears to have happened to Mars. The presence of our unusually large moon creates tidal forces that may have been essential for life's emergence from the oceans onto land. The moon also stabilizes Earth's axial tilt, preventing dramatic climate shifts that could have made the evolution of complex organisms impossible. The probability of Earth acquiring such a large moon through a random collision appears to be extraordinarily low. These Earth-specific conditions layer on top of the fine-tuning we observe in fundamental physics to create what seems like an almost impossibly improbable set of circumstances. Each additional requirement narrows the range of possible universes or planetary systems that could support life, making our existence seem increasingly miraculous. The mathematical precision involved in these various forms of fine-tuning has led some scientists to conclude that design is the most reasonable explanation for what we observe. The Nobel Prize-winning physicist Steven Weinberg noted that the cosmological constant's remarkably low value might be explained by a benevolent creator who fine-tuned it for life. The astrophysicist Fred Hoyle, after discovering the precise nuclear resonance needed for carbon production in stellar cores, declared that the evidence overwhelmingly pointed to a super-intellect who had designed the universe for life. But not all scientists interpret these observations as evidence for design. The same mathematical precision that suggests intentional calibration can also be explained through alternative mechanisms that don't require intelligence or purpose. These alternative explanations are often even more mind-bending than design theories, suggesting that we live in one of countless universes, or that the apparent fine-tuning is an inevitable consequence of natural selection operating on cosmic scales. The tension between design and naturalistic explanations for fine-tuning has created one of the most profound debates in contemporary science. This debate touches on fundamental questions about scientific methodology, the nature of explanation, and the relationship between physics and philosophy. It forces us to confront whether science can ever provide ultimate explanations for existence, or whether some questions lie beyond the reach of empirical investigation. As we continue our exploration of these extraordinary cosmic coincidences, we'll need to examine both sides of this debate with equal rigor. The evidence for fine-tuning is compelling and mathematically precise, but the alternative explanations are equally sophisticated and may ultimately prove more scientifically satisfying. The question we're investigating isn't just whether the universe appears designed, but what that appearance means, and whether we can ever know for certain which interpretation of the evidence is correct. The journey ahead will take us deep into cutting-edge physics and cosmology, but it will also require us to grapple with philosophical questions that have puzzled humanity for millennia. We're not just examining the technical details of cosmic fine-tuning, but exploring what these details might tell us about the nature of reality itself and our place within it. What makes this debate so fascinating is that both sides are working with the same extraordinary data. The numbers don't lie. The precision is undeniable. The question that keeps physicists and philosophers awake at night is what these numbers actually mean. Let's dive deeper into the specific mechanisms that had to align perfectly for carbon-based life to emerge anywhere in the universe. We're about to encounter what might be the most elegant example of apparent cosmic engineering ever discovered, hidden in the nuclear furnaces at the hearts of stars. In the 1940s, astronomer Fred Hoyle was investigating how the heavier elements formed inside stellar cores. He knew that stars could fuse hydrogen into helium, but creating carbon required something far more complex. Carbon nuclei contain 6 protons and 6 neutrons, and building them requires a process where 3 helium nuclei collide almost simultaneously in what's called the triple alpha reaction. The mathematical problem was staggering. The probability of 3 helium nuclei coming together at exactly the same instant should be virtually zero. Yet carbon exists in abundance throughout the universe, forming the backbone of every organic molecule we know. Something had to be making this impossible reaction not just possible, but routine. Hoyle realized that the only way this could work was if carbon nuclei had a very specific energy level that would create what physicists call a resonance. This resonance would act like a nuclear magnet, dramatically increasing the probability that 3 helium nuclei could stick together long enough to form stable carbon. But here's the remarkable part. Hoyle calculated exactly what this energy level would need to be, then convinced experimenters to look for it. They found it. The carbon nucleus has precisely the energy level that Hoyle predicted, now known as the Hoyle state. Without this exact resonance, stars would produce almost no carbon, and the universe would be filled with nothing but hydrogen and helium. No carbon means no organic chemistry. No organic chemistry means no life as we know it. But the story gets even more extraordinary. The same resonance that makes carbon production possible also had to be calibrated to avoid overproducing our oxygen. If the energy levels were slightly different, stellar fusion would convert all the carbon into oxygen before it could escape into space. Life requires both carbon and oxygen in specific proportions, and the nuclear physics inside stars delivers exactly that balance. The precision required for this cosmic chemistry set is breathtaking. The strong nuclear force that governs these reactions operates within a window that's less than 1% of its total possible range. Step outside that narrow corridor, and you get a universe with either no carbon at all or no oxygen to go with it. Either way, complex chemistry becomes impossible. Hoyle himself was so stunned by this discovery that he abandoned his lifelong atheism. A committed naturalist who had spent his career explaining cosmic phenomena through purely physical processes, he concluded that the evidence overwhelmingly pointed to what he called a super-intellect that had designed the universe specifically to produce carbon-based life. But carbon production represents just one thread in a tapestry of apparent design that extends from the quantum scale to cosmic horizons. Let's zoom out from stellar cores to examine how the universe's overall architecture seems calibrated for complexity and structure. The density of matter in the early universe had to fall within an incredibly narrow range for galaxies and stars to form at all. If the universe had been slightly denser, gravitational collapse would have created nothing but black holes. If it had been slightly less dense, matter would never have clumped together sufficiently to ignite stellar fusion. The critical density that separates these two fates is what cosmologists call the flatness problem. Our universe appears to sit exactly on this knife's edge. The actual density of matter and energy is so close to the critical value that cosmologists measure it with a parameter called omega, which equals 1 for a perfectly flat universe. Current observations suggest omega is 1.000, plus or minus a tiny uncertainty. This represents a level of precision that would be like balancing a pencil on its point for billions of years. The implications become even more staggering when you trace this precision back to the universe's earliest moments. In the first fraction of a second after the Big Bang, the density would have needed to match the critical value to more than 50 decimal places, deviate by even the smallest amount, and you either get immediate collapse or expansion so rapid that no structures ever form. This extraordinary fine-tuning extends to the cosmic microwave background radiation, the afterglow of the Big Bang that still fills space today. This radiation shows tiny temperature fluctuations that represent the seeds of all future cosmic structure. These fluctuations had to have exactly the right amplitude to eventually grow into galaxies and galaxy clusters, too small, and gravity would never overcome expansion to form structures. Too large, and the universe would be filled with massive black holes instead of stars and planets. The amplitude of these primordial fluctuations is characterized by a parameter called Q, which measures about 0.00001. This might seem like a small number, but it represents the perfect balance between cosmic smoothness and cosmic structure. Change Q by even a factor of 2 in either direction, and you get a universe that's either completely smooth or collapsed into black holes. Even the number of spatial dimensions in our universe appears to be precisely calibrated for complexity. We live in a universe with 3 dimensions of space and 1 of time. This 3 plus 1 dimensional structure seems so natural that we rarely question why it should be this way, rather than some other configuration. But mathematical analysis reveals that stable orbits and complex structures are only possible in exactly 3 spatial dimensions. In a universe with 2 spatial dimensions, Gravity would be too strong at short distances and too weak at long distances for stable planetary orbits. In 4 or more spatial dimensions, gravitational forces would make stable orbits impossible, and atomic nuclei would be unstable. Complex chemistry requires exactly the dimensional structure we observe. These examples represent just a small sampling of the apparent fine-tuning that permeates cosmic architecture. The list continues with the masses of elementary particles, the strengths of nuclear forces, the properties of dark matter, the rate of cosmic expansion, and dozens of other parameters that seem calibrated with impossible precision. Each new discovery in fundamental physics tends to reveal additional layers of apparent design rather than explaining away the coincidences we already know about. The more we learn about the universe's fundamental structure, the more remarkable the precision becomes. This accumulating evidence has forced even skeptical scientists to acknowledge that something extraordinary is going on. Steven Weinberg, hardly a proponent of design arguments, admitted that the values of physical constants seem to have been very finely adjusted to make possible the development of life. Martin Rees, one of Britain's most distinguished cosmologists, has identified 6 fundamental parameters that appear calibrated with extraordinary precision for the emergence of complexity and consciousness. The mathematical certainty of these observations creates a profound puzzle for naturalistic worldviews. If the universe emerged from purely random processes, the probability of getting all these parameters right simultaneously appears to be effectively zero. We're not talking about unlikely coincidences, but about precision that seems to require billions or trillions of random attempts to achieve even once. Yet here we are, embedded in what appears to be the one universe in countless trillions that happen to get everything exactly right. This situation would be like buying a single lottery ticket and winning jackpots on 1,000 different games simultaneously. Mathematically possible, but so improbable that alternative explanations become compelling. The design interpretation suggests that this precision reflects intentional calibration by some form of cosmic intelligence. This intelligence would need to possess an understanding of physics that far exceeds our current knowledge, capable of calculating the complex interactions between dozens of fundamental parameters to achieve the delicate balance that makes complexity possible. But the same observations that suggest design also provide the foundation for equally remarkable alternative explanations. Perhaps we don't live in a single, improbably fine-tuned universe, but in one member of an infinite collection of universes, each with different physical constants. In such a multiverse, the apparent fine-tuning would be explained by selection bias. We observe a life-friendly universe simply because we couldn't exist in any other kind. This multiverse hypothesis has gained significant support from developments in theoretical physics. Inflationary cosmology suggests that our observable universe might be just one bubble in an eternally inflating cosmic foam. String theory predicts an enormous landscape of possible universes with different physical laws. Quantum mechanics might require the continuous branching of reality into parallel worlds. If these theories are correct, then apparent design might be nothing more than an observational illusion. In an infinite multiverse containing every possible combination of physical constants, it becomes inevitable that some universes would have the right conditions for life. We find ourselves in one of these rare, life-friendly regions, not because of design, but because that's the only type of universe where observers could exist to notice the apparent fine-tuning. The multiverse explanation is elegant and mathematically sophisticated. It transforms the improbable into the inevitable without requiring intelligence or purpose, but it also raises profound questions about the nature of scientific explanation and the limits of empirical investigation. Multiverses are, by definition, unobservable from our position within a single universe. We cannot travel to other bubble universes to verify their existence or measure their physical constants. This makes multiverse theories inherently untestable by normal scientific standards. Critics argue that invoking unobservable entities to explain fine-tuning is no more scientific than invoking an unobservable designer. The debate between design and multiverse interpretations of fine-tuning reflects deeper tensions about what constitutes acceptable scientific explanation. Both approaches attempt to account for the same extraordinary observations, but they do so through fundamentally different conceptual frameworks. Design arguments suggest that apparent fine-tuning reflects genuine fine-tuning by an intelligent agent capable of setting physical constants with extraordinary precision. This explanation is conceptually straightforward and doesn't require exotic physics beyond our current understanding, but it introduces intelligence and purpose into cosmology, concepts that many scientists find incompatible with naturalistic methodology. Multiverse theories maintain naturalistic assumptions by explaining apparent design through purely physical processes operating across vast ensembles of universes. But these theories require accepting the existence of unobservable realities and may ultimately be untestable by scientific methods. The choice between these interpretations might ultimately depend on philosophical commitments about the nature of scientific explanation rather than empirical evidence alone. Both approaches are consistent with the mathematical precision we observe in cosmic fine-tuning. The question is which type of explanation we find more compelling given our broader understanding of reality. As we continue exploring these profound questions, we'll examine specific mechanisms that might generate multiverse scenarios and investigate whether these theories truly resolve the fine-tuning puzzle or simply push it back another level. We'll also explore new experimental approaches that might make seemingly untestable ideas scientifically accessible. The stakes of this investigation extend far beyond academic cosmology. The questions we're examining touch on the deepest issues of human meaning and cosmic purpose. How we interpret the apparent design in nature's fundamental structure affects how we understand our place in the cosmic order and the significance of consciousness in an apparently vast and mostly lifeless universe. Whether we're dealing with cosmic design or cosmic coincidence, the evidence forces us to grapple with possibilities that stretch the boundaries of human comprehension. But before we can properly evaluate these competing explanations, we need to understand just how recently science has discovered this extraordinary precision in nature's architecture. The recognition of cosmic fine-tuning is remarkably new in the history of human thought. As recently as the 1960s, most physicists assumed that the fundamental constants of nature could take on a wide range of values, without dramatically affecting the universe's ability to support complexity. The prevailing view was that life was robust enough to emerge under many different physical conditions. This comfortable assumption began crumbling as scientists developed more sophisticated models of stellar evolution, nuclear physics, and cosmic structure formation. Each advance in our understanding revealed new dependencies, new requirements, new ways that life seemed to depend on incredibly specific physical conditions. The breakthrough moment came when researchers began asking a deceptively simple question: what would happen if we changed just one fundamental parameter while keeping everything else the same? The answer, repeated across dozens of independent studies, was consistently shocking. Almost any change, no matter how small, led to universes that were sterile and lifeless. Consider what happens if we adjust the strength of the electromagnetic force by just a few percent. Atoms would either bind too tightly or too loosely to form the stable configurations needed for complex chemistry. Stars would burn either too hot and fast or too cool and slow to provide stable energy sources for billions of years. The nuclear reactions that forge heavy elements in stellar cores would either proceed too rapidly, creating nothing but iron peak elements, or too slowly, leaving the universe filled with nothing but hydrogen. These aren't speculative possibilities based on uncertain physics. They're concrete mathematical consequences derived from our most successful theories about how nature operates at fundamental levels. When you plug slightly different values for physical constants into the equations that govern stellar evolution, nuclear physics, and cosmic expansion, you consistently get universes that cannot support complexity of any recognizable kind. The precision becomes even more remarkable when you examine how multiple parameters must be coordinated simultaneously. It's not sufficient for each force or constant to be individually fine-tuned. They must be fine-tuned relative to each other in ways that create stable, long-lived systems capable of evolution and complexity. The ratio between the electromagnetic force and gravity, for instance, must fall within a narrow window for stars to exist at all. If electromagnetism were too strong relative to gravity, stars would be small, hot, and short-lived. If gravity were too strong relative to electromagnetism, stars would be massive, unstable, and prone to collapse into black holes before they could nurture planetary systems for billions of years. But even having stable stars isn't sufficient. The nuclear physics inside those stars must be calibrated to produce the right mixture of elements for complex chemistry. The expansion rate of the universe must be tuned to allow sufficient time for stellar nucleosynthesis, while preventing either premature collapse or expansion so rapid that galaxies never form. These interdependencies create what physicists call a fine-tuning problem. Each parameter constrains the others, creating a multidimensional space of possible universes where only a tiny fraction can support the emergence of complexity, structure, and life. The mathematical characterization of this problem has become increasingly sophisticated as computational power has allowed researchers to explore vast parameter spaces systematically. Modern studies can vary dozens of fundamental constants simultaneously and map out the regions of parameter space that permit various levels of cosmic complexity. The results are consistently striking. Whether you're looking at the conditions needed for stable atoms, long-lived stars, or complex chemistry, the viable regions of parameter space occupy tiny fractions of the total possibilities. We appear to live in a universe that sits in the narrow intersection of all these constraints, a cosmic sweet spot that permits the richest possible development of structure and complexity. This situation would be extraordinary enough if it involved just one or two coincidences, but the catalogue of apparent fine-tuning now extends to dozens of independent parameters, each calibrated with precision that seems to defy explanation through chance alone. The discovery of dark energy in the late 1990s added another layer to this puzzle. Observations of distant supernova revealed that the universe's expansion is accelerating, driven by some form of repulsive energy that fills space itself. This dark energy is characterized by the cosmological constant, the parameter that creates the most dramatic fine-tuning problem in all of physics. The cosmological constant represents the energy density of empty space. Quantum mechanics predicts that this vacuum energy should be enormous, roughly 120 orders of magnitude larger than what we actually observe. If quantum theory were correct about vacuum energy, the universe would have expanded so rapidly that no structures could ever have formed. Instead, we observe a cosmological constant that's almost exactly zero, but not quite. It's small enough to allow 13.8 billion years of cosmic evolution, but large enough to eventually overcome matter and radiation to drive accelerating expansion. This represents a level of fine-tuning that physicists describe as the most unnatural thing ever measured in science. The magnitude of this problem becomes clear when you consider what it would take to explain the cosmological constant through pure chance. You would need to specify its value to more than 120 decimal places to match observations. This is like randomly selecting a single atom from all the matter in the observable universe, and somehow picking exactly the right one. Yet here we are, living in a universe where this impossible precision has somehow been achieved. The cosmological constant has exactly the value needed for cosmic evolution to proceed from simple initial conditions to the complex structures we observe today, including galaxies, stars, planets, and conscious observers capable of measuring the cosmological constant itself. This situation creates what philosophers call the fine-tuning puzzle. The mathematical precision is undeniable, confirmed by multiple independent measurements and theoretical calculations. But the interpretation of this precision remains deeply controversial, dividing scientists into camps that seem irreconcilable in their basic assumptions about reality. One response to fine-tuning has been to search for deeper physical principles that might explain why the constants have the values they do. Perhaps what appears to be arbitrary precision actually reflects deeper symmetries or conservation laws that constrain the possible values of fundamental parameters. This approach has motivated decades of research into unified field theories, theories of everything, and fundamental symmetries that might reduce the apparent arbitrariness in nature's constants. String theory, supersymmetry, and grand unified theories all represent attempts to show that the fundamental parameters we observe are actually the only values consistent with deeper physical principles. These research programs have achieved remarkable mathematical sophistication and have revealed deep connections between apparently unrelated aspects of physics. But they have not succeeded in explaining why the fundamental constants have life-friendly values rather than values that would make complexity impossible. In fact, many of these theories have made the fine-tuning problem worse rather than better. String theory, for instance, appears to permit an enormous landscape of possible universes with different physical laws. Rather than explaining why our universe has life-friendly constants, string theory suggests that universes with completely different constants are equally fundamental and mathematically consistent. This has led many physicists to abandon hope of finding a unique theory that explains why our universe has the specific properties we observe. Instead, they've embraced the possibility that our universe is just one member of a vast multiverse where every possible combination of physical constants is realized somewhere. The multiverse hypothesis transforms the fine-tuning problem from a puzzle about unique cosmic design into a problem about selection bias and observation. If every possible universe exists somewhere in a vast multiverse, then it becomes inevitable that some universes will have conditions suitable for life. We find ourselves in one of these rare, life-friendly regions, not because of design or deeper physical principles, but because that's the only type of universe where observers could exist to notice the apparent fine-tuning. This explanation is mathematically elegant and preserves naturalistic assumptions about cosmic evolution. It doesn't require intelligence, purpose, or violation of physical laws. It simply requires that reality be much vaster and more diverse than we previously imagined. But the multiverse hypothesis also raises profound questions about scientific methodology and the nature of explanation. Multiverses are, by their very nature, unobservable from our position within a single universe. We cannot travel to other bubble universes to verify their existence or measure their physical constants. This makes multiverse theories inherently difficult to test by normal scientific standards. Critics argue that invoking unobservable entities to explain fine-tuning violates basic principles of scientific reasoning. If we allow theories to postulate unlimited numbers of unobservable universes to explain inconvenient observations, where do we draw the line? What prevents science from degenerating into unfalsifiable speculation? Supporters of multiverse theories respond that unobservability doesn't necessarily disqualify scientific theories. Many successful theories in physics postulate entities that cannot be directly observed, from quarks and gluons to black hole interiors and the multiverse of quantum mechanics. The criterion for accepting theories should be their explanatory power and mathematical consistency, not whether every prediction can be directly tested. This debate reflects deeper tensions about the nature of scientific explanation and the criteria for accepting theories about ultimate reality. Both design and multiverse interpretations attempt to account for the same extraordinary mathematical precision in cosmic fine-tuning, but they do so through fundamentally different conceptual frameworks that carry different implications for how we understand science, reality, and our place in the cosmic order. The design interpretation suggests that the precision we observe in fundamental physics reflects genuine fine-tuning by an intelligence capable of setting physical constants with extraordinary accuracy. This explanation is conceptually straightforward and doesn't require exotic physics beyond our current understanding. It treats the apparent design in nature as evidence for actual design, following the same logical principles we use to infer design in human artifacts. But design arguments face significant challenges in scientific contexts. They introduce intelligence and purpose into cosmology, concepts that many scientists find incompatible with naturalistic methodology. They also raise difficult questions about the nature and motivations of any cosmic designer. What kind of intelligence could set physical constants with such precision? Why would such an intelligence create a universe that appears to operate through natural laws rather than direct intervention? The multiverse interpretation maintains naturalistic assumptions by explaining apparent design through purely physical processes operating across vast ensembles of universes. It preserves the mechanistic worldview that has driven scientific progress for centuries, while providing a framework for understanding why our universe seems so improbably well-suited for complexity and consciousness. But multiverse theories also face significant challenges. They require accepting the existence of unobservable realities that may be inherently untestable. They raise questions about what it means to explain observed phenomena by postulating infinite numbers of unobserved phenomena. And they may ultimately push the fine-tuning problem back another level rather than solving it. If multiverses exist, what determines the mechanism that generates them? Why should the multiverse generating process produce universes with the right statistical properties to make life-friendly universes inevitable? The fine-tuning problem might simply migrate from the level of individual universes to the level of multiverse-generating mechanisms. Recent developments in theoretical physics have begun to provide more concrete frameworks for evaluating these competing interpretations. Advances in inflationary cosmology, string theory, and quantum gravity have made specific predictions about multiverse scenarios that might eventually be testable through astronomical observations. The cosmic microwave background radiation, for instance, might contain subtle signatures of collisions with other bubble universes. The distribution of galaxies might reveal patterns that reflect the multiverse structure within which our universe is embedded. Future gravitational wave detectors might be sensitive enough to detect echoes from parallel realities. These potential observations wouldn't necessarily resolve the debate between design and multiverse interpretations, but they could provide empirical constraints on multiverse theories that have previously been purely speculative. If specific multiverse scenarios make testable predictions that turn out to be false, it would strengthen the case for alternative explanations of fine-tuning. Meanwhile, advances in artificial intelligence and computational modeling are allowing researchers to explore fine-tuning in unprecedented detail. By simulating cosmic evolution under different assumptions about fundamental physics, scientists can map out the conditions needed for various levels of complexity and test whether apparent fine-tuning is as severe as it initially appears. Some of these studies have suggested that the requirements for complexity might be less stringent than previously thought. Perhaps life could emerge under a wider range of physical conditions than carbon chauvinism assumes. Perhaps the apparent precision in cosmic fine-tuning reflects selection effects in how we define complexity rather than genuine constraints on cosmic evolution. Other studies have confirmed and extended the fine-tuning observations, revealing new dependencies and narrower windows for viable cosmic evolution. The debate continues as both observational and theoretical capabilities advance, providing new ways to test ideas that once seemed beyond the reach of empirical investigation. The philosophical implications of this debate extend far beyond academic cosmology. How we interpret the apparent precision in cosmic fine-tuning affects fundamental questions about the nature of scientific explanation, the role of consciousness in cosmic evolution, and the meaning of existence itself. If the universe is designed, it suggests that consciousness and intelligence play fundamental roles in cosmic architecture. We would be not accidental byproducts of meaningless physical processes, but intended outcomes of purposeful cosmic engineering. This interpretation provides a framework for understanding human significance that resonates with deep intuitions about meaning and purpose. If the universe is one member of an infinite multiverse, it suggests that consciousness might be a rare but inevitable outcome of natural selection operating across vast ensembles of possible realities. We would be products of cosmic evolution rather than cosmic engineering, but our existence would still represent something remarkable and precious in the context of mostly lifeless, multiversal reality. Both interpretations assign special significance to consciousness and complexity, while maintaining very different assumptions about the underlying nature of reality. The choice between them might ultimately depend on philosophical commitments about naturalism, design, and the proper scope of scientific explanation rather than empirical evidence alone. As we continue exploring these profound questions, we'll examine the specific ways that Earth itself appears fine-tuned for life, investigating whether our planet's remarkable habitability reflects cosmic design, cosmic coincidence, or something else entirely. The precision we've observed in fundamental physics extends to astronomical and geological scales, creating layers upon layers of apparent fine-tuning that challenge our understanding of accident and necessity in cosmic evolution. The evidence we'll encounter forces us to grapple with possibilities that stretch human comprehension to its limits. Whether we're witnesses to the greatest coincidence in cosmic history or participants in the most elaborate design project ever conceived, the precision we observe in nature's architecture demands explanation that goes far beyond anything our species has previously contemplated. The story of Earth's apparent design extends far beyond the fundamental constants of physics into realms that become increasingly difficult to dismiss as mere coincidence. When we examine our planet's position in space and time, we discover layer after layer of conditions that had to align with mathematical precision for life to not only emerge but flourish for billions of years. Let's begin with something so fundamental that we rarely question it: the distance between Earth and our star. We orbit the Sun at an average distance of 93 million miles, a measurement astronomers call 1 astronomical unit. This might seem like an arbitrary number until you realize that this distance places Earth in an incredibly narrow zone where liquid water can exist on a planetary surface. Move our planet just 5% closer to the Sun, and Earth becomes Venus, a hellish greenhouse world where surface temperatures reach 900 degrees Fahrenheit, hot enough to melt lead. The oceans boil away into space, leaving behind a thick atmosphere of carbon dioxide that traps heat so efficiently that the planet's surface glows red hot even on the night side. Move Earth just 20% farther from the Sun, and we become Mars. A frozen desert where water exists only as ice or vapor, where the thin atmosphere provides no protection from deadly cosmic radiation. The average temperature plunges to -80 degrees Fahrenheit, making complex chemistry virtually impossible on the surface. This habitable zone, sometimes called the Goldilocks zone, represents a thin shell around every star where temperatures are just right for liquid water chemistry. For a star like our Sun, this zone extends from roughly 90 million miles to about 120 million miles from the stellar surface. Earth sits comfortably within this narrow range. But the precision required becomes even more remarkable when you consider how this zone changes over time. Our Sun has been gradually brightening throughout its 4.6 billion year lifetime. Early in Earth's history, the Sun was about 25% dimmer than it is today. This means the habitable zone was closer to the Sun in the past and has been slowly moving outward as our star evolves. For liquid water to remain stable on Earth's surface throughout geological time, our planet had to be positioned exactly where this migrating habitable zone would remain suitable for billions of years. This represents a form of temporal fine-tuning that extends the spatial precision we've already discussed. It wasn't sufficient for Earth to be in the right place at one moment in cosmic history. Our planet had to be positioned where it would remain in the continuously changing habitable zone for the entire 4.6 billion year period needed for complex life to evolve. But orbital distance represents just the first requirement in a cascade of conditions that had to align perfectly for habitability. Earth's size turns out to be calibrated with equal precision. Our planet has exactly the right mass to retain a substantial atmosphere while avoiding the runaway greenhouse effects that plague more massive worlds. If Earth was significantly larger, its stronger gravitational field would capture and retain enormous amounts of hydrogen and helium from the early solar system. We would end up with a thick atmosphere dominated by these light gases, creating crushing surface pressures and temperatures that would make liquid water impossible. This is what happened to the gas giant planets in our outer solar system. If Earth were significantly smaller, its weaker gravity couldn't hold on to atmospheric gases over geological timescales. Solar wind and thermal escape would gradually strip away our atmosphere, leaving us with the thin, cold conditions we observe on Mars today. The narrow range of planetary masses that permit stable, moderate atmospheres represents another layer of apparent fine-tuning. Earth's rotation rate provides yet another example of precise calibration. Our planet spins on its axis once every 24 hours, creating day-night cycles that moderate temperature extremes and drive atmospheric circulation patterns crucial for climate stability. This rotation rate appears to be nearly optimal for habitability. If Earth rotated much faster, say with 6-hour days, the increased centrifugal force would flatten our planet significantly and create extreme weather patterns with winds reaching hundreds of miles per hour. The rapid day-night cycling would create temperature swings so severe that complex ecosystems couldn't establish stable patterns. If Earth rotated much slower, say with month-long days, one side of the planet would bake under continuous sunlight while the other froze in permanent darkness. The extreme temperature differences would drive massive atmospheric circulation that would create planet-wide dust storms and weather patterns incompatible with the stable conditions needed for complex life. Our 24-hour rotation period sits in the narrow window that provides optimal climate stability, but this raises a puzzle about how Earth acquired this apparently perfect spin rate. Planetary rotation speeds are typically determined by the random collisions that occur during planet formation. The fact that Earth ended up with nearly ideal rotation timing seems remarkably fortunate. The mystery deepens when we examine Earth's axial tilt, the 23.5-degree angle between our planet's rotation axis and its orbital plane around the Sun. This tilt creates our seasonal cycles, with different hemispheres receiving varying amounts of solar radiation as Earth orbits the Sun. Without this tilt, there would be no seasons, No migration of climate zones, no periodic changes that may have driven evolutionary adaptation and complexity. But axial tilt, like rotation rate, should be essentially random based on the chaotic collisions during planetary formation. The fact that Earth has a moderate tilt that creates seasons without extreme climate variations represents another apparent coincidence in our planet's design for habitability. More remarkably still, Earth's axial tilt remains stable over geological time because of our unusually large moon. Most planets either have no moons or small moons that provide little gravitational stabilization. Without our moon's stabilizing influence, Earth's axial tilt would vary chaotically over millions of years, creating dramatic climate changes that would make the long-term evolution of complex life extremely difficult. The moon itself represents perhaps the most extraordinary coincidence in Earth's habitability story. Our satellite is proportionally larger compared to its parent planet than any other moon in the solar system except Pluto's Charon. The moon contains about 1.2% of Earth's mass, giving it sufficient gravitational influence to stabilize our planet's rotation and create the tidal forces that may have been essential for life's transition from sea to land. The leading theory for the moon's formation involves a Mars-sized object colliding with the early Earth at precisely the right angle and speed to blast material into orbit that eventually coalesced into our satellite. The probability of such a collision occurring with exactly the right parameters appears to be extraordinarily low, yet it apparently happened at just the right time in Earth's formation to create optimal conditions for future habitability. The moon's gravitational effects extend far beyond axial stabilization. Tidal forces caused by the moon's gravity create the ocean tides that expose and submerge coastal regions twice daily. These tidal zones may have provided crucial environments where early life forms could experiment with surviving periodic exposure to air, eventually leading to the colonization of land. The moon also drives internal heating in Earth through tidal flexing, contributing to plate tectonics and the geological processes that regulate our planet's climate over geological timescales. Without this additional energy source, Earth might have become geologically dead much earlier in its history, similar to what appears to have happened to Mars. But even having the right orbital distance, planetary size, rotation rate, axial tilt, and large moon isn't sufficient for habitability. Earth also needed to develop a powerful magnetic field that deflects the charged particles streaming from the sun in the solar wind. Without this magnetic shield, our atmosphere would be gradually stripped away over millions of years. Earth's magnetic field is generated by electrical currents flowing in our planet's molten iron core. This dynamo effect requires precise conditions, the right planetary size to maintain a molten core, the right composition to provide conducting materials, and the right rotation rate to organize the fluid motions into coherent magnetic field patterns. The strength of Earth's magnetic field appears to be calibrated within narrow limits for optimal habitability. Too weak, and solar wind would strip away our atmosphere. Too strong, and the field would trap dangerous radiation particles, creating deadly radiation belts that would sterilize the surface. Mars provides a sobering example of what happens when magnetic protection fails. Early in its history, Mars had a substantial atmosphere and possibly liquid water on its surface, but the planet's small size allowed its core to cool and solidify, shutting down the magnetic dynamo. Without magnetic protection, solar wind gradually stripped away the Martian atmosphere, leaving the cold, dry world we observe today. Earth's atmospheric composition represents another layer of apparent fine-tuning. Our atmosphere contains about 21% oxygen, 78% nitrogen, and trace amounts of other gases, including the carbon dioxide that drives photosynthesis. This mixture provides exactly the right conditions for complex oxygen-breathing life while maintaining chemical stability over geological time. the oxygen concentration is particularly critical. If atmospheric oxygen dropped below about 15%, fires couldn't burn, and many large animals couldn't survive. If oxygen rose above about 25%, spontaneous combustion would make forests and grasslands impossible to maintain. The current level sits comfortably within the narrow window that supports complex ecosystems while preventing runaway oxidation. But free oxygen is chemically reactive and should disappear from planetary atmospheres within a few million years unless continuously replenished. Earth maintains its oxygen-rich atmosphere only because photosynthetic organisms continuously produce oxygen faster than geological processes can remove it. This requires a delicate balance between biological and geological oxygen cycling that has persisted for over 2 billion years. The nitrogen that makes up most of our atmosphere serves crucial functions in moderating atmospheric chemistry and providing raw materials for biological processes. Nitrogen is relatively inert, which prevents it from interfering with oxygen-based metabolism, but it can be converted into biologically useful compounds by specialized organisms. This creates nitrogen cycles that support terrestrial ecosystems while maintaining atmospheric stability. Even the trace gases in Earth's atmosphere appear precisely calibrated for habitability. Carbon dioxide concentrations affect global temperature through the greenhouse effect. Too little CO2 and Earth freezes into a snowball state. Too much, and we get runaway greenhouse heating like Venus. Earth's CO2 levels are regulated by complex feedback mechanisms involving weathering, volcanism, and biological processes that maintain temperatures suitable for liquid water. Water vapor provides another greenhouse gas that helps regulate Earth's climate, while ozone in the upper atmosphere shields the surface from a deadly ultraviolet radiation. The delicate balance between all these atmospheric components creates what scientists call Earth's climate system, a complex network of feedback mechanisms that has maintained habitable conditions for billions of years despite external changes. The geological processes that regulate Earth's long-term habitability depend on plate tectonics, the slow movement of crustal plates driven by heat from Earth's interior. Plate tectonics serves multiple functions essential for life. It recycles carbon between the atmosphere and Earth's interior. It creates the continental land masses where terrestrial life can flourish, and it generates the chemical diversity needed for complex ecosystems. Plate tectonics requires precise conditions to operate effectively. Earth needed the right size to maintain sufficient internal heat, the right composition to create density contrasts that drive plate motion, and the right amount of surface water to lubricate plate boundaries. Too little internal heating and plates freeze in place like on Mars. Too much heating and the surface becomes too hot and unstable for life like on Venus. The timing of Earth's geological evolution also appears remarkably well coordinated with biological requirements. The heavy bombardment that battered the inner solar system early in its history ended just in time for life to emerge and establish itself. If this bombardment had continued longer, sterilizing impacts would have prevented life from gaining a foothold. If it had ended much earlier, Earth's surface might have cooled too rapidly to drive the chemical evolution needed for life's emergence. Earth's position in the Milky Way galaxy provides yet another layer of apparent fine-tuning. Our solar system orbits in what astronomers call the galactic habitable zone, a region far enough from the galactic center to avoid disruptive gravitational effects and intense radiation, but close enough to have access to the heavy elements forged in stellar cores. Near the galactic center, frequent supernova explosions and interactions with other stars would disrupt planetary systems and bombard planets with lethal radiation. In the outer regions of the galaxy, there are too few heavy elements to form rocky planets like Earth. Our solar system sits in the narrow annular region where conditions are optimal for the formation and long-term stability of habitable worlds. Even our solar system's architecture appears designed for Earth's habitability. The giant planets Jupiter and Saturn act as cosmic vacuum cleaners, using their powerful gravity to capture or deflect asteroids and comets that might otherwise impact Earth. Jupiter's position and orbital characteristics appear nearly optimal for protecting the inner solar system, while avoiding gravitational perturbations that would destabilize Earth's orbit. Computer simulations suggest that solar systems with different giant planet configurations typically either fail to protect terrestrial planets from impacts or gravitationally eject them from habitable zones. The specific arrangements we observe, with Jupiter and Saturn in particular orbital resonances, appears to provide maximal protection for Earth-like worlds. The age of our solar system also appears precisely calibrated for complex life. At 4.6 billion years old, our system has existed long enough for complex life to evolve, but not so long that our Sun has evolved beyond the stable main sequence phase. Stars more massive than the Sun burn out too quickly to allow time for complex evolution. Stars less massive than the Sun have habitable zones so close to the stellar surface that planets become tidally locked, with permanent day and night sides. Our Sun's stability over billions of years depends on its having exactly the right mass to burn hydrogen at a steady rate, without the dramatic variability that characterizes many other stars. This stability provides the consistent energy source needed for the long-term evolution of complex ecosystems. The chemical composition of Earth also appears fine-tuned for habitability. Our planet has exactly the right abundance of radioactive elements to provide internal heating for billions of years, while avoiding excessive radiation that would sterilize the surface. The ratio of silicon to iron in Earth's composition created the differentiated structure with a metallic core and rocky mantle that enables both magnetic field generation and plate tectonics. Even the abundance of water on Earth appears precisely calibrated. Too little water, and our planet would be a desert world where life could never emerge from isolated pools. Too much water, and Earth would be a global ocean world with no continents to support terrestrial ecosystems and the chemical cycling that drives biological complexity. Earth's water content is thought to have been delivered by comets and asteroids during the late heavy bombardment period. The timing and intensity of this water delivery had to be precisely calibrated to provide optimal ocean coverage without creating conditions that would prevent the emergence of continents through volcanic and tectonic processes. The temperature history of early Earth also required precise calibration to allow life's emergence. The planet had to cool sufficiently from its initial molten state to allow liquid water to condense, but not so much that it froze solid. This required a delicate balance between the heat generated by radioactive decay, the cooling effect of space, and the greenhouse warming from early atmospheric gases. Recent research has revealed additional layers of apparent fine-tuning in Earth's biological evolution itself. The transition from simple prokaryotic cells to complex eukaryotic cells appears to have required an extraordinarily improbable event where one cell engulfed another in a successful symbiotic relationship. This endosymbiotic event, which created the mitochondria that power complex cells, seems to have occurred only once in Earth's entire history, despite billions of years of opportunity. The evolution of photosynthesis, which created the oxygen-rich atmosphere needed for complex life, required the development of molecular machinery so sophisticated that its emergence seems almost miraculous. The photosynthetic apparatus uses quantum mechanical effects to capture solar energy with nearly perfect efficiency, suggesting engineering principles that exceed human technological capabilities. The emergence of multicellular life required solving complex problems of cellular cooperation and coordination that game theory suggests should be nearly impossible to achieve. Yet life found solutions to these problems repeatedly, creating the diverse ecosystems that support the biosphere we observe today. Even the timing of major evolutionary transitions appears remarkably well coordinated with Earth's changing conditions. The emergence of oxygen-producing photosynthesis coincided with the need to replace hydrogen-based early metabolism. The evolution of complex cells occurred just as Earth's atmosphere became oxidizing. The colonization of land happened precisely when atmospheric ozone levels became sufficient to provide ultraviolet protection. These biological coincidences layer on top of the physical and chemical fine-tuning to create what appears to be an integrated system designed for the emergence and maintenance of complex life. Each level of organization, from fundamental physics to planetary characteristics to biological evolution, seems precisely calibrated to work together in supporting the rich biosphere we observe today. The cumulative improbability of all these conditions aligning perfectly appears to be astronomically small. We're not dealing with a single, unlikely coincidence, but with dozens of independent requirements that all had to be satisfied simultaneously. The mathematical product of all these individual probabilities suggests that Earth-like conditions should be virtually impossible to achieve through random processes alone. Yet here we are, embedded in what appears to be the result of the most elaborate cosmic engineering project ever conceived. Every breath we take, every step we take on solid ground, every moment we spend under the protection of our magnetic field represents participation in systems that seem designed with extraordinary precision and foresight. This situation creates the same interpretive puzzle we encountered with fundamental physics, but now extended to astronomical, geological, and biological scales. Either we are witnessing the most extraordinary series of coincidences in cosmic history, or we are participants in a designed system that operates through natural laws to create and maintain conditions suitable for complex life. The design interpretation suggests that Earth's habitability reflects intentional calibration by an intelligence capable of coordinating physical processes across enormous scales of space and time. This intelligence would need to understand not just fundamental physics, but also stellar evolution, planetary formation, atmospheric chemistry, and biological evolution, well enough to create integrated systems that function harmoniously for billions of years. The naturalistic interpretation maintains that apparent design reflects selection bias, combined with natural processes operating over cosmic timescales. In a large enough universe with enough planetary systems, it becomes inevitable that some worlds will have the right combination of conditions for life, regardless of how improbable those conditions might be for any individual planet. But the selection bias explanation faces significant challenges when applied to Earth's specific characteristics. Unlike the fundamental constants of physics, which might vary between different universes in a multiverse, Earth's properties are determined by processes operating within our single universe according to fixed physical laws. The formation of our solar system, the collision that created our moon, the development of Earth's magnetic field, and the emergence of photosynthesis all occurred through natural processes operating under the same physical laws we observe today. These aren't free parameters that could be different in other universes, but outcomes of specific historical events that happen to occur in ways that optimized Earth's habitability. This suggests that Earth's fine-tuning might reflect something more than mere selection bias. Perhaps natural processes operating under our universe's physical laws have inherent tendencies toward creating habitable conditions. Perhaps the same forces that fine-tuned fundamental physics also guide cosmic evolution toward complexity and life. Alternatively, perhaps we drastically underestimate how many planets exist in our universe, and how often apparently improbable events actually occur when given sufficient opportunities. Recent discoveries of thousands of exoplanets have revealed that planetary systems are common throughout the galaxy, suggesting that Earth-like worlds might be more numerous than previously thought. But current observations also suggest that Earth's combination of characteristics might be extremely rare, even among potentially habitable planets. Most exoplanets discovered so far orbit much closer to their stars than Earth does to the Sun. Many orbit red dwarf stars that produce intense flare activity, potentially harmful to life. Very few appear to have the large moons that stabilize axial tilt and drive tidal effects. The more we learn about exoplanetary systems, the more unusual Earth's characteristics appear to be. This ongoing research will be crucial for determining whether Earth represents a common outcome of cosmic evolution or an extraordinarily rare combination of conditions that might occur only once in billions of planetary systems. Recent advances in astrobiology are beginning to provide new ways to test these competing interpretations. The James Webb Space Telescope and other next-generation instruments will soon be capable of analyzing the atmospheric compositions of potentially habitable exoplanets, searching for biosignatures that might indicate the presence of life. If life turns out to be common among Earth-like planets, it would support naturalistic interpretations of Earth's habitability. The apparent fine-tuning would reflect robust natural processes that reliably produce habitable conditions given sufficient time and opportunity. If life turns out to be extremely rare, even among apparently suitable planets, it would strengthen the case that Earth's habitability reflects something beyond natural selection operating on cosmic scales. The precision we observe in Earth's characteristics would represent genuine fine-tuning that requires explanation through design, deeper physical principles, or mechanisms we haven't yet discovered. The stakes of this investigation extend far beyond academic astrobiology. How we interpret Earth's apparent design affects fundamental questions about human significance, cosmic purpose, and the role of intelligence in cosmic evolution. If Earth is designed, we are participants in a purposeful cosmic project. If Earth is a cosmic accident, we are extraordinarily fortunate beneficiaries of natural processes that operated without foresight or intention. Both interpretations assign special significance to Earth and its biosphere, while maintaining very different assumptions about the underlying nature of cosmic evolution. The choice between them might ultimately depend on philosophical commitments about design, purpose, and the proper scope of scientific explanation, rather than empirical evidence alone. As we prepare to examine the philosophical frameworks that scientists use to interpret these extraordinary observations, we stand at the intersection of science and philosophy, where empirical precision meets ultimate questions about meaning and purpose. The Anthropic principle, which we'll explore next, represents science's most sophisticated attempt to grapple with the apparent design we observe at every level of cosmic organization. Whether this principle resolves the fine-tuning puzzle or simply provides a framework for thinking about irreducible mysteries, it forces us to confront the deepest questions about observation, existence, and the relationship between consciousness and the physical universe that gives rise to it. The precision we've discovered in cosmic architecture challenges our understanding of accident and necessity in ways that stretch human comprehension to its limits. But these same discoveries also provide unprecedented opportunities to investigate questions that previous generations could only address through speculation and faith. We stand at a unique moment in human history where empirical precision meets ultimate mystery, where scientific observation encounters the deepest questions about cosmic purpose and design. The answers we discover may transform not just our understanding of Earth's place in the cosmos, but our comprehension of what it means to be conscious observers in a universe that appears against all reasonable expectations to be perfectly calibrated for our existence. The Anthropic principle emerged in the 1970s as scientists grappled with these extraordinary observations. Coined by physicist Brandon Carter, this principle comes in two primary forms that offer radically different interpretations of cosmic fine-tuning. The weak anthropic principle suggests a simple, observational constraint. We observe a universe compatible with our existence because we couldn't exist in any other kind. This seems almost trivially true until you consider its implications. If the universe contained observers, it must possess the properties that make observers possible. We shouldn't be surprised to find ourselves in a life-friendly cosmos, because that's the only type of universe where surprise is possible. But the strong anthropic principle ventures into far more controversial territory. It suggests that the universe must have the properties that allow life to develop at some point in its history. This interpretation implies that observer-friendly conditions aren't just coincidental, but somehow necessary or inevitable. The distinction between these interpretations might seem subtle, but it carries profound implications for how we understand cosmic evolution and our place within it. The weak version treats fine-tuning as an observational selection effect, while the strong version suggests that fine-tuning reflects deeper principles about the nature of reality itself. Consider how this plays out in practice. When we observe that the cosmological constant has exactly the value needed for structure formation, the weak anthropic principle says this shouldn't surprise us because we couldn't exist in universes with different values. The strong version suggests that universes somehow must have values compatible with complexity and consciousness. Recent developments in theoretical physics have given new urgency to these debates. String theory, our most ambitious attempt to unify all fundamental forces, predicts an enormous landscape of possible universes with different physical constants. Some estimates suggest there could be 10 to the power of 500 different types of universes, each with its own set of physical laws. This string landscape provides a concrete framework for multiverse scenarios. If all these different universes actually exist somewhere, then our apparent fine-tuning becomes a statistical inevitability rather than evidence for design. With 10 to the power of 500 universes to choose from, some would inevitably have conditions suitable for life, and we necessarily find ourselves in one of those rare, observer-friendly regions. The mathematical elegance of this explanation has attracted many physicists. It preserves naturalistic assumptions while explaining apparent design through purely physical processes operating across vast ensembles of realities. No intelligence or purpose required, just natural selection operating on cosmic scales. But multiverse theories face formidable challenges that go to the heart of scientific methodology. These alternative universes are, by definition, causally disconnected from our own. We cannot travel to them, communicate with them, or gather direct evidence for their existence. This makes multiverse theories inherently difficult to test by traditional scientific standards. Critics argue that invoking infinite numbers of unobservable universes to explain fine-tuning violates the principle of parsimony that has guided scientific progress for centuries. Why postulate countless unobservable realities to avoid the possibility of design? Doesn't this represent exactly the kind of unfalsifiable speculation that science is supposed to avoid? The debate intensifies when you examine what multiverse theories actually require to solve the fine-tuning problem. It's not sufficient to simply postulate that multiple universes exist. You need a mechanism that generates universes with the right statistical properties to make life-friendly conditions inevitable. This mechanism itself would need to be fine-tuned. The multiverse generator would need to produce universes that explore parameter space efficiently enough to hit the narrow targets that permit complexity. If the generation process were biased towards sterile universes, then even an infinite multiverse might never produce observers. This shifts the fine-tuning problem from the level of individual universes to the level of multiverse-generating mechanisms. Instead of asking why our universe has life-friendly constants, we're asking why the multiverse has life-friendly generation processes. The apparent design problem might simply migrate to a higher level rather than disappearing entirely. Some physicists have attempted to address this concern by developing what they call landscape anthropics. These theories attempt to calculate the probability distributions for different types of universes within specific multiverse scenarios, determining whether observer-friendly conditions would be rare or common outcomes. The results have been mixed. Some calculations suggest that typical observers in multiverse scenarios would find themselves in universes very different from our own, with physical constants that barely permit complexity. Other studies conclude that universes like ours represent probable outcomes given reasonable assumptions about multiverse generation mechanisms. These technical debates reflect deeper philosophical tensions about the nature of scientific explanation. Multiverse theories ask us to accept that the fundamental explanation for our existence lies in realms forever beyond empirical investigation. This challenges traditional notions about what constitutes legitimate scientific theorizing. Meanwhile, design arguments face their own methodological challenges. Inferring design from apparent fine-tuning requires making assumptions about the intentions and capabilities of hypothetical designers. What kind of intelligence could calibrate physical constants with such extraordinary precision? Why would such an intelligence choose to operate through natural laws rather than direct intervention? These questions push design arguments beyond the boundaries of empirical science into theological and philosophical territory. While the precision we observe in cosmic fine-tuning is mathematically undeniable, interpreting this precision as evidence for intentional design requires assumptions about intelligence and purpose that science cannot directly address. The tension between empirical observation and ultimate explanation becomes particularly acute when we examine specific examples of apparent cosmic engineering. The production of carbon in stellar cores provides perhaps the most dramatic case study in the entire fine-tuning debate. When Fred Hoyle discovered the nuclear resonance that makes carbon production possible, he was forced to confront the extraordinary precision required for this process to work. The energy levels involved had to be calibrated to within tiny fractions of their total range to produce carbon in the quantities needed for complex chemistry. Hoyle's response was to abandon his lifelong commitment to naturalistic explanations and conclude that the evidence overwhelmingly pointed to intelligent design. A super-intellect had monkeyed with physics, he declared, and there are no blind forces worth speaking of in nature. But other physicists interpreted the same observations very differently. Rather than seeing evidence for design, they saw confirmation that our universe must be one member of a vast ensemble where every possible combination of physical constants is realized somewhere. The carbon resonance exists not because of intelligent calibration, but because we couldn't exist in universes where it doesn't. This interpretive divide illustrates how the same empirical observations can support radically different conclusions depending on one's philosophical assumptions about the nature of reality and explanation. The precision is undeniable, but its meaning remains profoundly contested. Recent experimental developments have begun to provide new ways of testing these competing interpretations. Advanced computer simulations allow researchers to explore how cosmic evolution would proceed under different assumptions about fundamental physics, mapping out the regions of parameter space that permit various levels of complexity. These studies have confirmed that the requirements for structure formation are indeed extraordinarily restrictive, change most fundamental constants by even small amounts, and you get universes that cannot support stars, planets, or the chemical processes that make life possible. But the simulations have also revealed that the constraints might be somewhat less severe than early studies suggested. Some forms of complexity and organization appear possible under a wider range of physical conditions than previously thought. This doesn't eliminate the fine-tuning problem, but it might reduce its severity. Observational astronomy is also beginning to provide new constraints on multiverse theories. If our universe is part of an eternally inflating multiverse, there might be detectable signatures in the cosmic microwave background radiation from collisions with other bubble universes. Several research groups are actively searching for these collision signatures, which would appear as circular patterns of temperature fluctuations in the microwave background. So far, no convincing detections have been reported, but the searches are ongoing with increasingly sensitive instruments. Future gravitational wave detectors might provide another avenue for testing multiverse scenarios. Some theories predict that collisions between bubble universes would generate gravitational waves with distinctive frequency signatures that could be distinguished from other astrophysical sources. These potential observations wouldn't necessarily resolve the debate between design and multiverse interpretations, but they could provide empirical constraints on specific multiverse models that have previously been purely theoretical. The philosophical implications of this debate extend far beyond academic cosmology into questions that affect how we understand human meaning and cosmic purpose. If the universe is designed, consciousness and intelligence play fundamental roles in cosmic architecture. We are intended outcomes of purposeful cosmic engineering rather than accidental byproducts of meaningless physical processes. This interpretation provides a framework for understanding human significance that resonates with deep intuitions about meaning and purpose. It suggests that our capacity for wonder, creativity, and moral reasoning reflects intended features of cosmic design rather than evolutionary accidents. But the design interpretation also raises difficult questions about the nature and motivations of any cosmic designer. Why create a universe that appears to operate through natural laws? Why allow suffering and extinction to play such prominent roles in cosmic evolution? Why make design so subtle that it requires sophisticated physics to detect? These theological puzzles have no easy answers and push design arguments beyond the realm of empirical science into philosophy and religion. While the precision we observe might suggest design, interpreting that precision requires making assumptions about intelligence and purpose that cannot be directly tested. The multiverse interpretation maintains naturalistic assumptions while still assigning special significance to consciousness and complexity. We are products of cosmic evolution rather than cosmic engineering, but our existence represents something remarkable and precious in the context of mostly sterile multiversal reality. This perspective suggests that consciousness might be a rare but inevitable outcome of natural selection, operating across vast ensembles of possible realities. We are not the intended purpose of cosmic evolution, but we represent one of its most extraordinary achievements. Yet multiverse theories also face profound challenges in explaining why conscious observers should exist at all. If most universes in a multiverse are lifeless, why should the generation mechanism produce any observer-friendly regions? The statistical arguments that make observer-friendly universes inevitable also seem to predict that most observers would find themselves in barely habitable conditions very different from what we actually observe. This observer problem has led some researchers to develop more sophisticated versions of multiverse theory that attempt to predict not just the existence of observers, but their likely characteristics and environments. These calculations become extraordinarily complex and often depend on controversial assumptions about the nature of consciousness and observation. The debate between design and multiverse interpretations reflects deeper tensions about the proper scope of scientific explanation and the relationship between physics and philosophy. Both approaches attempt to account for the same extraordinary mathematical precision, but they do so through fundamentally different conceptual frameworks. Design arguments treat apparent fine-tuning as evidence for actual fine-tuning by an intelligence capable of calibrating physical constants with extraordinary precision. This explanation is conceptually straightforward and follows the same logical principles we use to infer design in human artifacts. Multiverse theories explain apparent design through selection effects, operating across vast ensembles of universes with different physical constants. This preserves mechanistic assumptions about cosmic evolution while providing a framework for understanding why our universe seems so improbably well suited for complexity. The choice between these interpretations might ultimately depend on philosophical commitments about naturalism, design, and the nature of scientific explanation rather than empirical evidence alone. Both approaches are consistent with the mathematical precision we observe in cosmic fine-tuning. Recent developments in artificial intelligence and machine learning have begun to provide new perspectives on these ancient questions. As we develop increasingly sophisticated systems capable of recognizing patterns and inferring design in complex data, we gain new tools for analyzing the apparent precision in cosmic architecture. Machine learning algorithms trained on examples of designed and natural systems show interesting patterns when applied to cosmological data. Some analyses suggest that the parameter combinations we observe in fundamental physics bear signatures characteristic of intentional optimization rather than random selection. Other studies reach different conclusions, finding that apparent design signatures can emerge naturally from selection processes operating over sufficient timescales and with adequate sampling of parameter space. These computational approaches don't resolve the fundamental interpretive questions, but they provide new quantitative frameworks for analyzing them. The emergence of artificial general intelligence might eventually provide even more sophisticated tools for analyzing cosmic fine-tuning. Systems capable of understanding and modeling complex physical processes could potentially evaluate design and multiverse hypotheses with unprecedented rigor. But even the most advanced AI systems would face the same fundamental limitations that constrain human analysis of these questions. The interpretation of apparent design depends on philosophical assumptions about intelligence, purpose, and the nature of explanation that cannot be resolved through empirical observation alone. As we stand at this crossroads between empirical precision and ultimate mystery, the questions raised by cosmic fine-tuning continue to challenge our deepest assumptions about reality. Whether we are witnesses to the greatest coincidence in cosmic history or participants in the most elaborate design project ever conceived, the precision we observe forces us to grapple with possibilities that stretch human comprehension to its limits. The mathematical certainty of fine-tuning observations provides a foundation of shared evidence that both design and multiverse theorists must address. But the interpretation of this evidence remains profoundly contested, reflecting different visions of cosmic purpose, human significance, and the proper boundaries of scientific explanation. Perhaps the most remarkable aspect of this debate is how it brings together cutting-edge physics and ancient philosophical questions in ways that illuminate both domains. The precision we've discovered in cosmic architecture forces us to confront ultimate questions about existence, purpose, and meaning that have puzzled humanity throughout its history. Whether the universe is designed or accidental, whether consciousness represents intended outcome or evolutionary accident, the evidence compels us to recognize that we inhabit an extraordinary reality where the conditions for complexity and awareness exist against enormous odds. This recognition carries profound implications for how we understand our responsibilities as conscious beings in a cosmos that appears, against all reasonable expectations, to be perfectly calibrated for our existence. The Anthropic principle, in all its forms, reminds us that our very ability to contemplate these questions represents something precious and perhaps unprecedented in cosmic history. The debate between design and multiverse interpretations will likely continue as long as humans retain the capacity for wonder about their place in the cosmic order. But regardless of which interpretation ultimately proves correct, the precision we observe in nature's architecture stands as testimony to the extraordinary nature of existence itself. In a universe where consciousness can emerge to contemplate its own origins, where intelligence can discover the mathematical principles governing reality, where wonder and curiosity can drive beings to ask ultimate questions about purpose and design, we find ourselves participants in something remarkable beyond ordinary comprehension. The anthropic principle, whether weak or strong, design-based or multiverse-grounded, points toward the same fundamental recognition. We exist in a reality so precisely calibrated for complexity and consciousness that our presence here represents either the most extraordinary coincidence imaginable or evidence for cosmic purposes that transcend our current understanding. This recognition transforms every moment of conscious experience into participation in cosmic mystery, every act of scientific discovery into exploration of apparent design, every question about meaning and purpose into investigation of our place in an architecture that spans from quantum scales to cosmic horizons. The precision continues to unfold before us, layer upon layer of apparent calibration that challenges our assumptions about accident and intention in the deepest structures of reality. Whether this precision reflects design or coincidence, purpose or probability, it confronts us with questions that reach to the very foundations of existence and meaning in a universe that seems, against all odds, to have been waiting for conscious beings capable of recognizing its extraordinary mathematical elegance. But the anthropic principle itself faces challenges that cut to the heart of how we understand scientific reasoning and cosmic coincidence. When we examine the logic more carefully, we discover that the principle might not resolve the fine-tuning puzzle as elegantly as it initially appears. Consider a thought experiment that philosophers call the firing squad scenario. Imagine you're standing before a firing squad of 50 expert marksmen. They fire simultaneously, but somehow every bullet misses. You find yourself alive and unharmed after what should have been certain death. Now you could apply anthropic reasoning and say, well, of course all the bullets missed, because if they hadn't, I wouldn't be here to observe the outcome. This reasoning is technically correct, but it hardly explains why such an extraordinarily improbable event occurred. Most people would suspect that something more than mere chance was involved. Perhaps the marksman deliberately aimed to miss. The cosmic fine-tuning situation presents a similar logical structure. Yes, we necessarily observe a universe compatible with our existence, but this observation doesn't eliminate the puzzle of why such an improbable configuration exists in the first place. The anthropic principle tells us that we shouldn't be surprised to find ourselves in a life-friendly universe, but it doesn't explain why life-friendly universes exist at all. This limitation becomes more apparent when we examine specific examples of fine-tuning with quantified probabilities. The cosmological constant appears calibrated to 1 part in 10 to the power of 120, a precision so extreme that getting it right by chance would be like blindfolding yourself and throwing a dart that hits a target the size of a proton somewhere in the observable universe. Even if we accept that we necessarily observe values compatible with our existence, the sheer magnitude of the precision raises questions that pure selection reasoning cannot address. Why should any universe exist with constants calibrated to such extraordinary accuracy? Why should the space of possible universes contain any regions suitable for complexity at all? These questions push us toward what philosophers call the meta-fine-tuning problem. Even multiverse scenarios require their generation mechanisms to be calibrated in ways that make observer-friendly universes possible. The laws or principles that govern multiverse creation must themselves have properties that enable the production of life-compatible regions. Some physicists have attempted to address this challenge through what they term landscape statistics. These approaches try to calculate the probability distributions for different types of universes within specific multiverse frameworks, determining whether observer-friendly conditions represent likely or unlikely outcomes of natural generation processes. The calculations prove extraordinarily complex and often depend on controversial assumptions about the nature of probability in infinite ensembles. Different statistical approaches can yield radically different conclusions about whether our universe represents a typical or atypical outcome of multiverse generation processes. Max Tegmark has proposed what he calls the mathematical universe hypothesis, suggesting that all mathematically consistent structures exist as physical realities. In this framework, our universe exists not because it was designed or randomly generated, but because it represents one possible mathematical structure among infinitely many others. This approach sidesteps questions about multiverse generation mechanisms by postulating that existence itself is equivalent to mathematical consistency. Every possible set of physical laws exists somewhere in the space of mathematical structures, making our life-friendly universe inevitable rather than improbable. But the mathematical universe hypothesis faces its own conceptual challenges. If all possible mathematical structures exist as physical realities, then most conscious observers should find themselves in universes very different from our own, with minimal complexity barely sufficient for awareness. The fact that we observe a universe rich in structure and complexity becomes puzzling within this framework. Meanwhile, advances in computational cosmology have begun to provide more sophisticated tools for analyzing fine-tuning claims. Researchers can now simulate cosmic evolution under different assumptions about fundamental constants, mapping out the parameter spaces that permit various levels of structure formation. These studies have confirmed that the requirements for complexity are indeed remarkably restrictive, but they've also revealed some surprising flexibility in cosmic evolution. Certain types of structure and organization appear possible under a somewhat wider range of conditions than earlier studies suggested. For instance, recent simulations suggest that stellar formation might be possible even with significant changes to the strong nuclear force, though the resulting stars would have very different properties and lifetimes. Similarly, some forms of complex chemistry might emerge under alternative electromagnetic force strengths, though the specific molecular architectures would be unlike anything we observe on Earth. These findings don't eliminate fine-tuning concerns, but they do suggest that the requirements for complexity might not be quite as severe as the most dramatic fine-tuning arguments claim. The universe might be more robust to parameter changes than we initially realized, though still requiring significant calibration for optimal complexity. Observational astronomy continues to provide new constraints on both fine-tuning arguments and multiverse theories. The Planck satellite's precise measurements of the cosmic microwave background have revealed the universe's fundamental parameters with unprecedented accuracy, allowing more sophisticated tests of how sensitive cosmic evolution is to parameter variations. These observations have confirmed that our universe sits remarkably close to the boundary between different evolutionary fates. Small changes in the dark matter density or cosmological constant would lead to dramatically different cosmic histories, supporting claims about the precision required for structure formation. At the same time, searches for multiverse signatures in cosmological data continue with increasingly sensitive instruments. While no definitive evidence for other universes has been found, ongoing surveys are pushing toward the sensitivity levels where multiverse effects might become detectable if they exist. The James Webb Space Telescope has begun providing unprecedented views of the early universe, revealing how cosmic structure formed during the first billion years after the Big Bang. These observations offer new tests of whether the fine-tuning we observe was necessary for early structure formation, or whether alternative evolutionary pathways might have been possible. But perhaps the most intriguing developments are emerging from the intersection of artificial intelligence and fundamental physics. Machine learning algorithms are beginning to reveal unexpected patterns in cosmological data that human analysis might have missed. Some AI systems trained on simulated cosmic evolution under different parameter combinations show interesting capabilities for predicting which parameter ranges will produce complexity. These systems sometimes identify fine-tuning relationships that weren't obvious from traditional theoretical analysis. Other machine learning approaches are being applied to analyze the apparent design signatures in cosmic architecture. Algorithms trained to distinguish design from natural systems show mixed results when applied to cosmological parameters, with some analyses suggesting design-like patterns and others finding signatures consistent with natural selection processes. The emergence of increasingly sophisticated AI capabilities raises fascinating questions about how artificial intelligence might eventually approach the fine-tuning puzzle. Systems capable of modeling complex physical processes at unprecedented scales might be able to evaluate design and multiverse hypotheses with greater precision than human analysis allows. But even the most advanced computational analysis faces the fundamental limitation that interpretation of apparent design depends on philosophical assumptions about intelligence, purpose, and causation that cannot be resolved through empirical observation alone. The biological fine-tuning we observe on Earth adds another layer of complexity to these interpretive challenges. The emergence of life itself required what appears to be an extraordinary sequence of chemical innovations, from self-replicating molecules to photosynthesis to the complex cellular machinery that powers modern organisms. Each of these biological innovations seems to require specific chemical and physical conditions that had to be maintained over enormous timescales. The transition from simple chemical reactions to self-replicating systems represents a level of organizational complexity that seems almost impossible to achieve through random molecular interactions. The development of photosynthesis created the oxygen-rich atmosphere that enabled complex multicellular life, but this process required molecular machinery so sophisticated that its emergence appears nearly miraculous. The photosynthetic apparatus captures and converts solar energy with efficiency that approaches theoretical limits, suggesting optimization principles that exceed current human engineering capabilities. Even more remarkably, the timing of major biological innovations appears precisely coordinated with Earth's changing physical conditions. The emergence of oxygen-producing photosynthesis coincided with the need for new energy sources, as earlier chemical processes became less viable. The evolution of complex cells occurred just as atmospheric conditions became suitable for oxygen-based metabolism. These biological coincidences compound the physical fine-tuning we observe in cosmic architecture to create what appears to be an integrated system designed for the emergence and maintenance of life. Every level of organization, from fundamental physics to planetary characteristics to biological evolution, seems calibrated to work together in supporting complex ecosystems. The cumulative improbability appears staggering when you multiply together all the individual coincidences required. We're not dealing with a single, unlikely event, but with cascading sequences of apparent fine-tuning that span from quantum mechanics to global ecology. This situation creates profound challenges for naturalistic explanations that rely purely on chance and natural selection. While any individual coincidence might be dismissed as selection bias or statistical fluke, the systematic pattern of apparent optimization across multiple independent domains becomes increasingly difficult to explain without invoking either design or extraordinary luck. Yet the design interpretation faces equally significant challenges in explaining why apparent design operates through natural laws rather than direct intervention. If intelligence is responsible for cosmic calibration, why create a universe that appears to run itself through mechanical processes rather than requiring ongoing management? This hiddenness problem has puzzled design theorists for centuries. Why would a cosmic designer make the evidence for design subtle enough that sophisticated scientific analysis is required to detect it? Why not make design obvious through clear violations of natural law or unmistakable signatures of artificial intervention? Some philosophers argue that hidden design might be preferable to obvious design because it preserves human freedom and moral responsibility. If design were undeniable, it might coerce belief and eliminate the intellectual courage required for genuine, philosophical, and scientific inquiry. Others suggest that working through natural laws might represent a more elegant approach to cosmic engineering than direct intervention. A designer capable of calibrating physical constants to achieve desired outcomes through natural processes would demonstrate greater sophistication than one requiring constant miraculous intervention. But these theological speculations push design arguments beyond the realm of empirical science into philosophy and religion. While they offer potential explanations for the hiddenness of design, they cannot be tested through observational evidence or experimental investigation. The multiverse alternative maintains naturalistic assumptions while providing a framework for understanding apparent design through selection effects. If vast numbers of universes exist with different physical constants, then observer-friendly conditions become statistically inevitable rather than evidence for intentional calibration. This explanation preserves the mechanistic worldview that has driven scientific progress while accounting for the extraordinary precision we observe. No intelligence or purpose required, just natural selection operating on cosmic scales across vast ensembles of possible realities. But multiverse theories also face formidable conceptual challenges that go to the heart of scientific methodology. These alternative universes are causally disconnected from our own, making them inherently unobservable and potentially untestable by traditional scientific standards. Critics argue that invoking infinite numbers of unobservable entities to explain inconvenient observations violates principles of scientific parsimony. If we allow theories to postulate unlimited, unobservable realities to account for fine-tuning, where do we draw the line between legitimate scientific theorizing and unfalsifiable speculation? The testability problem becomes particularly acute when you examine what multiverse theories actually require to solve fine-tuning puzzles. It's not sufficient to simply assert that multiple universes exist. You need specific mechanisms for generating universes with appropriate statistical properties to make life-friendly conditions inevitable. These generation mechanisms must themselves be calibrated in ways that permit the production of observer-compatible regions. The multiverse generator needs exactly the right properties to explore parameter space efficiently enough to hit the narrow targets that allow complexity and consciousness. This shifts the design problem from individual universes to multiverse-generating processes. Instead of asking why our universe has life-friendly constants, we ask why multiverse generation mechanisms have life-friendly statistical properties. The apparent fine-tuning might migrate to a higher level rather than disappearing entirely. Recent theoretical work has attempted to address these concerns through more sophisticated multiverse models that attempt to derive generation mechanisms from fundamental physical principles rather than postulating them ad hoc. String theory landscape scenarios represent the most developed example of this approach. If string theory is correct, the enormous landscape of possible vacuum states might provide a natural framework for understanding multiverse generation. Different regions of the landscape would correspond to different types of universes, with the overall statistical properties determined by the mathematical structure of string theory itself. But string theory faces its own empirical challenges. Despite decades of intensive research, no experimental tests of string theory's distinctive predictions have been successfully performed. The theory remains mathematically elegant, but observationally unverified, raising questions about whether it provides genuine scientific explanation or sophisticated speculation. The landscape anthropic approach also faces what some researchers call the measure problem. In infinite multiverse scenarios, all possible outcomes occur infinitely often, making it difficult to calculate meaningful probability distributions for different types of observations. Different approaches to defining probability measures in infinite ensembles can yield contradictory conclusions about which types of universes and observers should be most common. Without solving the measure problem, multiverse theories cannot make definitive predictions about what typical observers should expect to find. These technical challenges reflect deeper philosophical tensions about the nature of scientific explanation and the criteria for accepting theories about ultimate reality. Both design and multiverse approaches attempt to account for the same extraordinary precision in cosmic architecture, but they do so through fundamentally different conceptual frameworks. Design arguments treat apparent fine-tuning as evidence for genuine calibration by intelligence capable of setting physical parameters with extraordinary precision. This follows familiar patterns of design inference that we use successfully in other contexts, from archaeology to forensic science to the search for extraterrestrial intelligence. Multiverse theories explain apparent design through selection effects operating across vast ensembles of realities with different physical constants. This preserves naturalistic assumptions about cosmic evolution while providing mechanisms for understanding why observer-friendly conditions might be inevitable rather than improbable. The choice between these interpretations might ultimately depend on philosophical commitments about naturalism, design, and the proper scope of scientific explanation rather than empirical evidence alone. Both approaches remain consistent with current observational data while pointing toward very different implications for cosmic purpose and human significance. Recent developments in experimental philosophy have begun to provide new insights into how people actually reason about fine-tuning arguments and anthropic explanations. Studies of intuitive responses to fine-tuning scenarios reveal interesting patterns in how design and coincidence explanations are evaluated by both experts and non-experts. These investigations suggest that design intuitions might be more robust than critics of anthropic reasoning assume. Even when people understand selection effects and anthropic constraints, they often continue to find design explanations more compelling than pure coincidence accounts when confronted with extreme fine-tuning scenarios. But psychological studies also reveal systematic biases in how people evaluate complex probabilistic arguments and assess evidence for design claims. Cognitive limitations might make us naturally prone to overinterpreting apparent patterns and underappreciating the power of selection effects in explaining seemingly improbable observations. The intersection of cognitive science and cosmological reasoning raises fascinating questions about whether human intuitions about design and coincidence provide reliable guides to cosmic truth. Our evolved psychology might be well adapted for detecting design in biological and social contexts, but poorly calibrated for evaluating evidence about fundamental physics and cosmic architecture. As we continue grappling with these profound questions about cosmic purpose and apparent design, new empirical developments promise to provide additional constraints on competing theoretical frameworks. The next generation of cosmological surveys will measure fundamental parameters with unprecedented precision, testing whether fine-tuning claims hold up under the most careful observational scrutiny. Advanced computer simulations will explore cosmic evolution under alternative parameter combinations with greater sophistication, mapping out the full space of conditions that permit various levels of complexity and structure formation. These studies will help determine whether apparent fine-tuning reflects genuine constraints on cosmic evolution or artifacts of limited theoretical understanding. Future searches for multiverse signatures will push towards sensitivity levels where bubble universe collisions or other multiverse effects might become detectable if they exist. While such signatures would not definitively resolve design versus multiverse debates, they would provide crucial empirical input to theoretical discussions that have previously relied primarily on mathematical speculation. The emergence of artificial general intelligence might eventually provide unprecedented capabilities for analyzing cosmic fine-tuning and evaluating competing explanations. Systems capable of processing vast amounts of cosmological data and modeling complex physical processes might identify patterns or relationships that human analysis has missed. But regardless of how these empirical and theoretical developments unfold, the fundamental questions raised by cosmic fine-tuning will likely continue challenging human understanding for generations to come. Whether the universe is designed or accidental, whether consciousness represents intended outcome or evolutionary fluke, the precision we observe forces recognition that we inhabit an extraordinary reality where conditions for complexity exist against enormous odds. This recognition carries profound implications for how conscious beings understand their responsibilities and significance in cosmic evolution. If we are products of intentional design, we might bear special obligations to fulfill the purposes for which we were created. If we are accidental outcomes of natural processes, we might carry unique responsibilities as the only known instances of cosmic self-awareness. Either interpretation suggests that consciousness and intelligence represent something precious and potentially rare in cosmic history. The mathematical precision that makes our existence possible, whether through design or coincidence, points toward the remarkable nature of awareness itself as a phenomenon that emerges from the deepest structures of physical reality. In contemplating these mysteries, we find ourselves at the intersection of empirical precision and ultimate wonder, where scientific observation meets philosophical questioning about meaning, purpose, and our place in an architecture that spans from quantum foundations to cosmic horizons. The fine-tuning we observe, whether evidence for design or extraordinary coincidence, stands as testimony to the remarkable nature of existence in a universe where consciousness can emerge to contemplate its own origins and wonder about the mathematical elegance that makes such contemplation possible. The questions we're wrestling with tonight extend far beyond the realm of pure science into territory where empirical observation meets the deepest mysteries of existence itself. As we stand at this crossroads between mathematical precision and ultimate meaning, we find ourselves confronting possibilities that challenge every assumption we've held about purpose, intelligence, and our cosmic significance. What makes this investigation so compelling is that we're not dealing with abstract philosophical speculation, but with concrete, measurable phenomena that have been verified by independent research teams across multiple disciplines. The fine-tuning we observe isn't a matter of interpretation or wishful thinking. It's mathematical fact, confirmed by decades of careful observation and theoretical analysis. Yet the implications of these facts remain profoundly contested, dividing the scientific community along lines that reflect not just different theoretical preferences, but fundamentally different worldviews about the nature of reality itself. We're witnessing a debate that cuts to the heart of how science should approach ultimate questions about existence and meaning. Consider the extraordinary situation we find ourselves in as conscious observers. We exist in a universe where the fundamental forces are calibrated with precision that defies comprehension. We inhabit a planet positioned with mathematical accuracy in space and time. We participate in biological systems that display engineering sophistication beyond our current technological capabilities. And we possess the cognitive capacity to recognize and investigate these remarkable coincidences. This self-referential aspect of cosmic fine-tuning adds another layer of mystery to an already profound puzzle. Not only do the physical conditions exist for complexity and consciousness to emerge, but conscious beings have developed the scientific capabilities needed to discover and measure the precision that makes their existence possible. We are the universe studying itself, matter organized in such a way that it can contemplate its own organization. This recursive relationship between observer and observed creates philosophical puzzles that push beyond the boundaries of traditional scientific methodology. The recognition of cosmic fine-tuning represents one of the most significant developments in human understanding since the scientific revolution. For the first time in our species' history, we possess detailed mathematical knowledge about the precise calibration required for our existence. We can quantify with extraordinary accuracy the narrow parameters within which complexity and consciousness become possible. This knowledge transforms age-old questions about cosmic purpose from matters of pure speculation into empirical investigations with measurable parameters and testable implications. Whether the universe is designed or accidental, the precision we observe provides concrete foundation for evaluating competing explanations. But perhaps most remarkably, this scientific revolution in understanding cosmic architecture has occurred during the same historical period when human consciousness has developed the capacity to contemplate its own cosmic significance. We are simultaneously discovering the mathematical precision that makes us possible and developing the philosophical frameworks needed to interpret what this precision might mean. This convergence of empirical discovery and existential questioning suggests that we might be living through a unique moment in cosmic evolution when intelligence has developed sufficient sophistication to recognize its own extraordinary circumstances while still maintaining the wonder and humility needed to ask ultimate questions about meaning and purpose. Tonight we've journeyed through the most extraordinary mystery in all of science, examining evidence that challenges everything we thought we knew about accident and intention in the cosmos. From the quantum precision of fundamental constants to the perfect positioning of our pale blue dot, we've discovered layer upon layer of apparent calibration that seems to transcend the boundaries of coincidence. Whether we're witnesses to the most elaborate cosmic engineering project ever conceived, or the most extraordinary series of accidents in the universe's history, one truth emerges with absolute certainty. We exist in a reality so precisely tuned for complexity and consciousness that our very presence here represents something remarkable beyond ordinary comprehension. The mathematics don't lie. The precision is undeniable, but the meaning remains beautifully, mysteriously contested. Perhaps that's exactly as it should be. In a universe capable of producing beings who can contemplate their own cosmic significance, wonder itself might be the most profound evidence of all. Until we meet again on another journey into the deepest mysteries of existence, keep looking up, keep questioning, and remember that every breath you take participates in the most extraordinary story ever told.